much, Asad, for the introduction. Thanks a lot to the organizers for the invitation. It's a great pity. I mean, it's a great pleasure to be here and a great pity I cannot be there. But for some sort of universal justice, the weather is being amazing this week in the United Kingdom, which is pretty much a miracle, to be honest. But I mean, without any further though, I would like to go into the topic of today's talk. I mean, it's about something I have been consistently brainwashing people during the last years, especially in this audience, which is this thing called the Landau-Ginzburg conformal field theory correspondence. So this is a physics result described, back in the late 80s, early 90s, by a bunch of physicists. I mean, just to mention a few: Vyacheslav, Warner, Emil Martinec, Ed Witten, Peter Ho, Peter West, predicting mathematically some. I mean, these can be more precise physically, but mathematically, which is what I'm interested. It states that there should be a certain relation between two different sorts of categories. Hope you're seeing there. Okay. Categories of representations. Of vertex operator algebras. So usually, nice enough kind, rational, so you confine it. I mean, this phenomenon tends to like supersymmetry, n equals 2 supersymmetry. Oops. On the one side, and then on the other side, this should be related in some way to something called matrix factorizations. So it's something which a priori doesn't seem, at least in my humble opinion, doesn't seem very trivial to see the connection between these two things. And well, yeah, we are trying to understand this because we don't know exactly how this relation works, to which extent, which ones, which not, and so on. And we want to compare these two kinds of categories at two levels. We want to compare them as C-linear categories. This corresponds to what physically is boundary conditions. And also, I would like to introduce a tensor product, if possible. So I would like to compare these two as tensor categories. Physically speaking, I will be comparing the effects. So as I said, I mean, how these two mathematical entities are connected, no idea exactly how this works. I mean, there's some physics literature stating, okay, this is how these two things should connect, and so on and so forth. But unfortunately, I mean, the current state of affairs is not totally optimistic. I mean, we have several examples available of C-linear equivalences. I have been involved in a bunch of those. I mean, with several collaborators up and down. Also, there's also some suggestions of how, of some equivalences in a little bit of an indirect way. But okay, it's in the C-linear level. Okay, we have a bunch of examples, great. But sadly enough, there's only so far one example for tensor equivalence, which I worked out with my two collaborators, Alexei Davidov and my PhD advisor, Ingo Honkel. So given this very sad perspective, I would like today to expand the main result of this article in here, because it's a tensor equivalence, but it's constrained to some, it depends on the set of parameter, and this only holds for the parameter being odd. So I would like to expand this for any value of this parameter. So evil plan for today. So in order to do that, I would like to, I'm not expecting everybody to be an expert on matrix factorizations, unlike the other side of the correspondence. I would like to give you a very brief introduction. I'm not going to assume a lot. Then I would like to state this main theorem, and then I would like to tell you a little bit about how, we managed to prove recently, how to, this equivalence holds for more parameters than we initially thought. I should have mentioned that this is joint work with Thomas Wasserman. Who is based at the University of Oxford. And in case you're hiring, let me just say he's an amazing mathematician and physicist. So, okay, let's start with this part. I am going to go really easy. I'm going to keep it really a very simple setting. You may find matrix factorizations in a variety of other contexts. In actually algebraic geometry, you can relate these to coherent sheaves. You can also find them in very highly representation theoretical topics like Cohen-Macaulay modules. But mainly because of physics restrictions, I'm going to just be super easy. I'm going to fix as my base field to be C. I am going to take my base string to be just a polynomial in n variables. And let me take one element in this polynomial ring. I am going to define this W to be what I call potential if it satisfies the following condition. If I compute the dimension of this quotient ring S divided by the ideal generated by the partial derivatives of W with respect to each of the variables of my ring, if this quotient ring is finite dimensional, then W is going to be what I call a potential. Let me give you an example to help you parse that. Easiest one I can think of. Let me just take S to be polynomial ring, one variable. This will be the easiest potential. So of course, you will get the Cx divided by the ideal generated by x to the minus 1, clearly finite dimensional. Here you go. All right, so if you give me one of these pairs of a polynomial ring and a potential on it, I can define what it is in matrix factorization of this potential. By the way, the name potential has a very physical motivation behind. Because it's actually this extra term interaction functional makes the characteristics that Landau-Ginzburg model you're dealing with. This matrix factorization consists of a pair M and the M, where this first component in here is where it's a free set gradient module. So because it's set graded, I will display this set grading like this. And the second component, M, it is going to be a degree 1 S-linear and by degree 1, I mean with respect to this set grading of M. So any morphism like this is going to be described by a 2 times 2 matrix with 0 entries in the trace and something here. But not any morphism will do. I want this guy to satisfy that if I compose this map twice with itself, what I'm going to recover is the identity of my module with the potential acting on one side. Because it's not, a proper differential by itself, I'm going to call this guy the twisted differential. And let me just follow up with the example from before. A proper matrix factorization of this potential in here will be the matrix factorization given by 2 copies of my base ring. And the twisted differential, it's going to be a 2 times 2 matrix of the shape where, I'm taking this K to be different from 0 and D to avoid the trivial matrix factorization. So, if you want to check, and you compose this guy twice with itself just by simple matrix multiplication, and then you will get x to the d times identity matrix, satisfying exactly the condition we need. So now that we have a matrix factorization, I can introduce what it's called a morphism of matrix factorization, because everything I want is like constructing a category, as I was modeling in the beginning. One can take morphism of matrix factorizations, given they choose such, to be an S-linear map from M to N, no further constraints. But actually, if you construct the category with these two as they stand now, you will get a very nice, actually it's a differential set to graded category, but I am going to be interested in actually the zero homology of this guy. And by this, let me just be a little bit precise. So my objects, I'm not going to change them. It's going to be the same as MF of W. So the fun is going to be at the morphism level. I'm going to consider only morphisms of degree 0. Remember, we have because of this set-graded grading of the my base module in the matrix factorization, any morphism I write down between two matrix factorizations will inherit this grading. So I'm going to choose only the degree 0 ones. So I'm going to take a morphism in MF of degree 0, and then I'm also analogously you can write down that this means it is compatible with the twisted differentials in that way. So okay, but there's 2 ways you can construct a morphism of matrix factorizations of degree 0. One, it is actually strictly degree 0, or it can be of degree 1 composed with a twisted differential, one of some twisted differential. So I want to exclude the second option, and for this, I'm going to mod out any G's in MF such that they have degree 1. Or, either because they are degree 1 by themselves, or by a composition of VMs and a morphism of degree 0. Great, so once I have this category here, I'm going to remark it. I would like to mention a couple of facts. So if I use bimodules instead of S modules, because I'm using left modules, I've used left modules in the previous definition for the sake of clarity. This has been also studied. Usually matrix factorizations, whenever you use bimodules, they call matrix bifactorizations, and the corresponding category is usually denoted HMF and BI, just to remark that actually, I mean, in this case, I mean, if you want to go in full generality, you can use two different potentials, but I'm just going to constrain myself to the case where I'm using both on the left and on the right the same potential, which is this category here. Let me explain a little bit with an example. Again, I'm going to follow up a little bit. So if you give me two pairs of a ring and a potential, sorry, a polynomial ring and a potential. So I'm going to take Cx and x to the d. Cy. I hear some side in there. Anybody has a question? I mean, please feel free to interrupt me if that's the case. So given these two, let me construct the following bimodule with the following twisted differential. So xy, two copies, dm. So nice. And so, I mean, whenever I have, I mean, the condition for the matrix, the category of matrix bifactorizations is that when you subtract the action on the left minus the action on the right. So, tiny remarking here, what I mean when I'm writing this in here is 9, I mean x to the y. But, you know, for the sake of simplicity, x to the d minus y to the d. This is actually quite a nice matrix factorization, and actually not exactly a very innocent choice of a first example, because this guy is actually, I mean, this matrix factorization is actually a tensor unit of this category here, but let me not get ahead of myself. Let me generalize a little bit the previous. I'm going to take M to be, again, two copies of this polynomial ring in two variables. And now, for my twisted differential, I am going to take the following product of linear factors of x to the d minus y to the d. With eta being a primitive fifth root of unity, I mean L can go between 0 and d minus 1, and M, I mean, again, root of unity. So, I mean, what I'm doing in here is actually, if you take x to the d and then I start writing down this. In this shape, what I'm doing is like taking consecutive blocks of this. Like, for example, if I take these 2 or like the 3 and so on, then I mean, my M will be 1 and then J will be 1. Because these guys actually appear in string theory. I'm going to give them a name because they're going to be absolutely important for us and for our purposes. I'm going to give them a name and some notation PML to remark these two parameters in here. And I'm going to refer to them as permutation type. Matrix factorization. Actually, it should be a bifactorization, but yeah, that's the case. And again, keep this one in mind because they're going to be important for us. So continuing with remarks, I mean, whenever we have bimodules, we can tensor any module. So given in this case, if you give me 3 pairs of a potential and a polynomial ring in a potential in it, and I construct a matrix bifactorization of one potential minus the other and another of the second and the third potential, I can tensor them. And how do you do this? Well, the tensor product matrix factorization is a factorization of W1 minus W3. So this W2 potential kind of gets canceled one with each other. And I mean, this guy in here is an S1, S3 bimodule. And the twisted differential in this case can be constructed in terms of the twisted differential of the matrix factorizations involved. So and you construct it like this. So, so for the case, as I was mentioning before, this category HMFBI, if I have W2, actually it would be W3. The same potential, HMF BI is monoidal. And actually, I should say that, I mean, the structure of these categories have been studying at length. We have a very good grasp of how they behave. And also, I mean, like there's a beautiful higher categorical construction gathering all the any possible HMFs BI that you can have in some by category of Landau-Ginzburg models that has very nice properties. I'm just going to, I mean, please ask me if you're curious. I'm just going to keep it brief for today. And let me also say that besides having a nice, well-defined tensor product, there's also duals that can be defined in a very explicit way. I mean, because I haven't constrained the rank of my modules, I mean, to finite rank, I should say that this is actually, of course, only works for finite rank matrix, something called finite rank matrix factorizations that needs to constrain the rank of your module. But I mean, let me just not go into too much detail and give you an example of how these guys work. And then let me say that, for example, the right dual of a permutation type matrix factorization is given by this permutation type matrix factorization. So I promised these guys were going to be important. So go. They're going to be very, very crucially important. I'm going to set PD to be the full subcategory of this HMFBI when I should say excuse me, consisting of objects which are isomorphic to direct sums of permutation type matrix factorizations. Direct sums, I also didn't give you any detail of what the direct sum of matrix factorization should be, but you can just take, I mean, what you're thinking, what you're suspecting this is. Actually, this is a very nice category, and one can state the following term about it. So PD is actually closed under tensor product. And explicitly, if you give me L and L prime in 0 and D minus 2, then I can tensor 2 such, and the fusion formula looks like this. L plus L prime 2D minus 4 minus L prime. This is new L minus L prime, step 2. And B M plus M plus 1/2 of L plus L prime is new. And if you're familiar, I mean, L looks suspiciously like SU2. I mean, it's the same fusion rule. But I really don't want to go into any more details. I mean, this is pretty much everything you need to understand the result I want to state today on the matrix factorization side. So let's go for it. I'm going to, on the representations of VOA side, I am going to denote as new the n equals 2 superconformal VOA. So the super VOA of the n equals 2 unitary minimal model with central charge given by this. This was at length studied by Drazen and Holtziger Berdil, just to mention a couple. Because it's super, of course, we can write the bosonic part and even the odd part. And I would like to state the following theorem. This is the Fröhlich, Fuchs-Runke, and Schweigert, that actually the kind of representations of this bosonic part can be realized as the subcategory. I'm going to say now something, and if you're not familiar with the vocabulary, it's fine. I'm just going to state an equivalent property. One can prove it's an equivalent property. So I'm going to take the subcategory of local modules over some commutative algebra. In the following. Product of categories. So CFD, I'm going to, this whole product, I'm going to give it the name of CFD. So this is going to be the triple, the Lie tensor product, SU2 plus 2. This is representations of U1, representations of U1, 4. So this guy, in this first guy in here, these are the integrable highest weight mod of the affine SU2. At the level D minus 2. And this 2, this is the category, this is the category of representations of, of U1, the VOA associated to U1, extended in some way. But I would like you to think of them today as, as pointed categories. So this means that they are equivalent to big G omega. If that helps. But anyways, I mean, with simples, I mean, the simples in this triple oh, sorry, I should have also mentioned that by this notation, I mean that I'm taking the opposite braiding and the ribbon twist of the category, of the original category. And I mean, the simples in this triple product, don't get too intimidated by it, are just, it's going to be something really simple. So LMS, where L takes values between 0 and t minus 2, M takes values in set to d, and S takes values in set 4. And this ugly condition here can be simply restated that L plus M plus S needs to be even. That's a nice category. The thing is that I'm interested in something like more micro, I mean something more internal than this big category. I am going to I'm going to extract the following two subcategories. I'm going to take the here as CNSD, the category of the, given by simples that satisfy that L plus M is even and S is even, still satisfying this conditioning here. And CR, I'm not going to need it today, but I'm going to request. So, if you have a physics inclination, you may recognize this as Neveu-Schwarz and Ramon sector. All right, so actually we have now all the ingredients I need, for stating the big, this big theorem. Well, not big theorem for me, it was very big, but and very special. But okay, stating this, the main theorem of this paper, this article. As a warming up, let me say that these two categories, PDT and CNS, were first proven by two physicists, Ilka Brunner and Daniel Roggenkamp, back in 2007, to be equivalent as C-linear categories. And well, we improve this result, stating that they were tensor equivalent. And shame on us for the odd only. And why the odd is actually because of the way the proof was constructed. So for the odd, we actually found the following equivalence of braided fusion categories. So CNS, FD, is actually splits in a product of two different categories. Again, I'm not going to go into too much detail of what these categories are, but at least I want to give you a flavor of the richness of this result. So this guy here, it's just such a great vector spaces. With trivial associator. So, there's not no omegas around. And this guy here, this big guy here, this is what this denotes the Tempel-Leib category. And this guy is actually, why I'm mentioning this explicitly, it's because it's actually generated by a self-dual object. And this generation is going to be important for us. by a self-draw object of dimension 2D, 2 cosine pt. And this thing down here, this is, I'm modeling out some morphisms generated by Bensel-Jones polynomial, the Bensel-Jones projector, sorry. Or Jones-Bensel, as James Turner likes to correct me. Okay, so the thing is that we use this splitting. I mean, we first noticed that CNS could split into these two categories. So using this, we construct a tensor product, sorry, a tensor functor. It was quite a process, actually. I mean, constructing this tensor product needed some work. We actually managed to boil it down into specifying small pieces of information, so that was good. CNS into D. I mean, we were using set to set the equivariant categories and whatnot. And I mean, and then using the semi-simplicity of the categories, diffusion rules, and this, I mean, the functor then managed to prove equivalence. All right, so the thing is that, I mean, clearly, because of the first step, the proof only works for D odd. And we were not really sure what happened in the even case. The thing is that, I mean, curiously, diffusion rules hold. I mean, by the way, diffusion rules were actually given by Brunner and Roggenkamp. We just managed, I mean, we just proved it. I mean, but diffusion rules hold for any value of D, and actually there was no physics obstruction telling us, okay, no, this should work. No, I mean, like, it was kind of clear if you check the literature that this should work altogether. It was just more like, what do we do now? Like, what's the maneuver here to go over this obstruction? Let me just write that down for you. So no physics. So, I mean, actually this resulting here was the biggest obstacle. So, I mean, danger, horrible. So, all right, I was banging my head for a bunch of years. And then Thomas and I mean, after discussing quite a bit, and luckily on time for the 7 years roll, because 2007, 2014, and then we managed to prove this at the end of last year. We managed to see that actually the equivalence holds true for any value of D. And like the trick, like what actually gave us the hint of what happens is actually this presence of vecset D. I mean, it's truly remarkable. I mean, you don't see, I mean, this is splitting from before. That's something actually special. So, and that gave us a hint of where to go and how to do this. Let me give you a sketch of our proof. So first I'm going to introduce a certain braiding for this, for this vecset D. And as you may guess, this is given by a quadratic form. CX, where you're sending pi square. And I'm going to denote just simply be, just because, I mean, because I want to, get in confusion between the braided and non-braided deck, I'm going to say except the equipped with this braiding. And then I'm going to use this extra braiding to show the following. So P to the D and CNS FD are braided module categories over this category V. And I'm defining this in the sense of Henrique's tenor. Henrique Penny's tenor. Back in 2015. So if you were never exposed to the concept of module category, let me just give it to you in a nutshell. So one way you can regard tensor categories is some kind of categorification of rings. So these module categories is like, it satisfies the same principle as you would use to construct a module over a ring. It will be the analogous concept, but at the categories level. Big constraints, a lot of data. Oh well, but hopefully you can get the idea. And actually having a module category is not, you may wonder, okay, that's very recent. Well, at least to me, I don't know, I lost track of everything since the pandemic. But actually, having this extra braiding, it imposes extra conditions up and down on the structure. Here in this paper of Andre, Dave, and James, they take care of what happens when you include this extra structure, and that's this. So the thing is that, okay, once we saw that this was actually happened, we noticed that these two categories, thanks to, it's like really exchangeable having these two notions. The braided module categories over B, or being enriched over V. Enrichments, if you never saw it, again, and in a nutshell, it's having a category that whose morphisms are objects in another category. So in this case, any morphisms I can have, they are braided vector spaces. So by the way, let me just remark that this notion of monoidal categories over braided monoidal categories enrich over monoidal categories. Monoidal categories enrich over a braided monoidal category. It's in the sense described by Scott and Dave. And actually, this was also generalized, to extend it by Corey Jones, Scott Morrison, Dave Pennis, and Julian Plavnik. But we only need this. So the great thing is that, yes, this gives us exactly monoidal categories enriched over braided monoidal category. But besides giving us a very nice path to connect to planar algebras and all this subfactor work, The thing is that this gives us key information concerning the generation of the category. Remember that in the first proof, we had this splitting thanks to, because we knew, we could find two generators that didn't, they will never intersect with one with each other. So here, this gave us like the way to go, knowing this. Remember, in this equivalence, we have the vector spaces and the rest of the category, which was generated by a single object. And using this V enrichment, we could claim that CNS, this is generated as a V enriched category by, again, a single object, and that with some morphisms. That actually, in the first case, they were, this object, excuse me, was a dual object. In this case, we think it's an algebra object. And I want to say some extra adjectives soon. So, and with all this at hand, like having this structure, we construct the functor as, a functor between two V-enriched categories. We construct this functor as V-enriched categories. So, we just, take this generator and then exhibit an image for the objects and the morphisms, making it an algebra object. And hopefully that's it. So, if I'm talking today about this, it's because, not only, because I think it's a beautiful theorem, altogether, but, it shows that there's like a lot of categorical structures arising in here. And I'm not completely sure it has been observed anywhere else. So, to conclude on my last 5 minutes, I would like to throw this question to you, to the audience. So, the CNS of D, also PT, PT. I'm not being, I'm just taking this one because it's actually the one related to VOAs. We have observed it has this very nice braided module category structure over, the braided vector spaces. We also have observed, analogously, that this category can be enriched over these vector spaces. So what I'm wondering lately, since we proved this, is that is there any other VOAs displaying similar structure? Having these structures, having these enrichments here and extensions thereof, it's quite a rare thing. It's not easy. So, this is like a nice result exactly because of this, because if we see this structure, which by itself is rare. And so, has anybody observed any splitting of the categories, any appearance of VecG or, VecG omega is kind of like a cheating in the sense that when we observe this in categories of representations of some VOAs, like the lattice VOAs, or in some results by Allen and Wood, they also proof, there's some pointed categories related to the Heisenberg VOA. But have you seen something like this? Because it's beautiful. And just to finish, I would like also to mention more things that I would like to do with this result. One question is like how, as I mentioned, there has been some work on G extensions yes, G extensions of this notion in here introduced. I mean, these monoidal categories enriched over a braided monoidal category. This was developed, as I mentioned, by Corey, Bascott, Dave, and Julia. So can we extend our result using this extension theory that we already know? So it's about computing the example and see how, if we can push forward a little bit, this result within the Landau-Ginzburg conformal theory correspondence. But again, I mean, this is always spinning around one example. Again, shame on us, shame on me. So I wonder, like, how can we extract more tensor equivalences, hopefully from the cases that we know of C-linear equivalences. It's a lot about extracting the good categories. So there we go. Something that Thomas and I are working on is, like, once we're done with this and hopefully putting the paper around the archive, because I have been, dear God, dreading about it. It's actually, we would like to use all this structure and start replicating results conjecture, described in the physics literature by Balfa and Barner concerning the minimal models, some catastrophic results apparently. And actually, I also have been putting this in many of my talks, but there's physical evidence for more equivalences beyond the minimal models. Actually involving the n=2 Kasama-Suzuki models. So hopefully another source of interesting relations between categories of representations of VOAs and these quite nice matrix factorizations. So I hope that was interesting. If you have any questions, please fire away. And for now, I'm just going to say muito obrigada pela atenção, or as we say here in Wales, diolch yn fawr. Thank you very much for your attention.
Thank you, Anna. Other questions in the audience?
I ask a question, Anna?
In Zoom?
Please go. Yeah. Hey!
How are you? Okay. Good to see you. Thank you for the lovely talk.
Thank you. I love your talk, by the way. I was going to ask you for your slides.
Well,
tell me.
Jethro has some, but I can send them to you.
Yeah.
I'd like a copy of your side or something. Yours are much prettier than mine. About this extension that you identified, so on the n=2 side, right, there's not very many candidates for an algebra object. Did you identify what it was? Is it related to some sort of ADE extension, or?
I'm not completely sure.
Was it a D-type extension?
Which one you mean? This?
Yeah, where you've identified an algebra object.
Yes. We have an idea, quite a clear idea of which object is this one. It's just it's a little bit of a generalization of the objects we had previously. It's just one needs to take into account extra parameters. It's a little bit more complicated, but it kind of reduces to the previous ones that we knew. More details in the paper as soon as it is ready. I'm going to make sure, I will make sure to share it with you when it's out there.
Fair enough.
I think I interrupted you.
No, that's fine.
Okay, great.
Did this result give you any more insight into why these n=2 categories are the correct categories? So in physics,
it just gave me marble somehow.
But the way it's presented, right? You just say, okay, the fusion rules on the matrix factorization side have this SL2e flavor, and then you fiddle about and say, oh, it's not SL2, it's actually n=2. But
yeah, it's kind of extending in a sense, but I'm not really sure why. How to select. Why this selects the nice category and how. I'm not completely sure yet. And I know I have been thinking about this for a while already. It's kind of like the hope that, if we expand a little bit on on this perspective of like treating this as separated module categories and so on. I mean, maybe this is going to help us understanding a little bit more, especially because if they are indecomposable, I mean, then hence equivalent to categories of modules over some algebras. Maybe there's something there to be said. But I mean, upcoming homework once we are done writing. So.
Okay, thanks again, Anna.
Not a problem. Thank you, David, for the question.
Are there other questions?
I don't think so in Zoom.
I guess everybody's tired and I'm the last of the day, so please have a caipirinha for me. Tell me.
Very naive question. So before you went to the specific examples, you made this general statement that these categories have a tensor product and joules and things. So are these in general fusion categories or braided fusion categories?
No, I mean, because we don't. No, I mean, I wish I had some more examples of fusion rules. I mean, of fusion categories within this context. I mean, and we don't even have semi-simplicity for HMFs.
Right.
So, which is cuts really. It really narrows down what I mean. It doesn't really narrow down the search. It's a little bit of the magic of it. I mean, why, for example, the permutation type matrix transitions are so special? Well, bingo, because it's one of the little instances that you can have of a fusion category.
Okay.
But I mean, it's not really. I mean, like finding fusion subcategories within HMF or HMF BI. That's a little bit the art of it, and why. I mean, another point of difficulty into finding more of these equivalences.
Okay, thanks.
Can you reconstruct the matrix factorization data directly from VOA?
I mean, in this particular case, yes. In any other cases, no idea. I mean, one thing I can reconstruct actually is, or I can try to reconstruct, is the central charge. So one of the things that physics tells you is that if you have, I mean, it is like a direct way of computing, of comparing the central charges from one and the other. I mean, there's a way, if you have a potential, there's a way of computing the central charge by assigning some Q grading to the variables involved. And this, you can compare it to the VOA. Beyond that, not much of an idea, besides what the physics tells us. I mean, there's some description on how to compare the boundary conditions, but mathematically precise, not that much more, unfortunately.
Okay, thank you.
So help me out. Not a problem. Thank you for the question.
If there are no more questions, let's thank the speaker again.
Thanks, everyone. Nice seeing you all.
Thank you, Anna. Bye.
Bye, guys. Have fun.